Hello, and welcome to this video where we will be expanding on the concept of quantum circuits. That is something which we have also seen in the video 2 of this series. So if you want to refresh your basics of that concept, you can go back to that video and watch it. So, what are quantum circuits? Now, let's begin with a very simple example. As you can see on the screen, we have blocks of input qubit to output qubit, and in between, we have what you call as quantum registers and quantum gates. So, let's begin on the left hand side from an input qubit. Traditionally, the input states, unless stated otherwise, are always initialized to qubit 0 state, and this is the traditional approach. You may have a different initialization if your application or if application demands it or you feel it necessary. So we start with the input qubit from the left hand side at the of the state 0, and then it flows through what is called as quantum resistor, or also can be called as quantum channel. Now, when it flows through the quantum register or channel, it is acted upon by something, what we call as a quantum gate. And the concept of quantum gate is something which we have seen in the last video of this series. And what it gives is then it will generate an output. In this case, it is changing the output to state 1 because we are applying what is called as an X quantum gate. So what is an X quantum gate? An X gate is nothing but it's something which is a simple matrix as indicated on the screen, and it is also called as a Pauli X matrix. And the only function it does is that when it acts upon a state, it changes or reverses the state for that particular qubit. What does it mean? For example, let's say the X gate is now being applied to qubit with a state 0, as you can see on the screen. And it is nothing more than now a matrix multiplication that we have seen in the quantum linear algebra session. So when you multiply this, the Pauli X matrix with the vector uh, uh, of qubit 0, which is a vector representation represented by 1 0, and when you do this multiplication, you will get what you call as 0 1, which is a vector representation of qubit 0 of qubit 1. Now we can extend this concept further. For example, now you can apply the X gate on the qubit state of 1, and you can also apply X gate twice on the qubit state of 0. And what we will get? In the first case, it reverses the state of the qubit from 1 to 0, and in the second case, since we are applying it twice, we will end up at the original input from where we started, so from 0 1 to 0 again. Now if you look at this very carefully, you can very easily draw the parallels from a classical logic gate circuit of NOT operator, because that is what the NOT operator also does, applies an input, or rather takes an input and gives you an output which is opposite to the input. So if you apply 0, you will get 1, you apply 1, you will get 0. So in that sense, these are very same. But now let's extend this concept to a superimposed state of qubits, and let's see what is the outcome. So what we are doing here is that instead of applying on a single qubit, here we are applying X gate on a qubit which is represented by the states as combination of state as represented in the bracket. So 1 by 2 under root 2 of state 0 plus 1 by 2 under root 2 of state 1. We can use the distributive property of calculating the gate logic here. And if you want to know what is a distributive property, please do see in the series on quantum linear algebra. But what we can do here is that when we expand this equation, you will see that the first part of the composed qubit state, which is represented by 0 getting changed to 1, and the second, which is represented by 1 getting changed to 0. However, algebraically, we can also rewrite this in the way move 0 to the left and the state 1 to the right, and we will end up getting the same thing as to what the input is. Now the question you have to ask yourself, in this case, does it really represent the NOT gate? Because mathematically, nothing has changed. The input has remained same as the output. So this is the key takeaway for you to have from this session, that applying a Pauli X on a superimposed or a composite qubit state may not mathematically change the output, unlike in the classical gate logic where the output do get changed. So I'll stop here and I'll hope to see you in the next video. Thank you very much.